All right, so last time we characterized two connected graphs. We gave two simple characterizations. Today, for three connected graphs, I'd like to give one characterization. We'll see another one when we see the full Menger's theorem, probably next lecture. Okay, so in order to do this, we need to, let's not use green. We need a definition here that's going to be useful outside of connectivity as well. This is a very, very useful definition, but this is the first time we see it in this class. It's what's called an edge contraction. I'll draw a figure and describe it here in a moment, but edge contraction in a graph is a simple idea where you grab an edge, pull its two endpoints together, and create a new vertex, and that vertex is adjacent to all the things that one or the other endpoints were adjacent to originally, okay? Just like you just squeeze an edge together, okay? So let E, X, so X, Y are the end vertices of E, be an edge in graph G, and then by, we'll denote it as follows. G with a little circle, X, Y, we denote the graph obtained by contracting, whatever that means, the edge E into a new vertex. Usually we call that vertex V sub E. There's no period there, which is adjacent to the vertices of G that were adjacent, I'll just say, use past tense here, were adjacent to X or Y, okay, or both. Usually, although not always, when we contract an edge, it can create multi-edges. I'll draw an example in a moment where you get multi-edges. Usually we ignore them. Usually when we do an edge contraction in a graph, we want to remain in a graph, and so we delete multi-edges. We also delete loops, which you can get as well. But we don't always do that. It depends on the problem we're working with. Sometimes it's convenient to leave loops and multi-edges behind, okay? So I'll say usually we delete loops and multi-edges, but not always, okay? All right, so let's look at a couple easy examples here. Let's see. Maybe the first one won't have any like weird stuff happening. So say this is our edge E here. Let me put it in red there. And so if I contract that edge, I'm going to get vertex V sub E, and all the other vertices that were in the graph remain. So there's 1, 2, 3, 4 other vertices. 1, 2, 3, 4. And I just keep any original adjacency, right? Any edges that were adjacent before remain adjacent. This one's not adjacent to this one, right? That's this vertex and this vertex. They're both adjacent to, maybe I should put VE in red. So this guy's adjacent to this because that's this edge here was adjacent to this end. This one was adjacent to that end as well, so it goes there. This one was not adjacent. Oh yeah, sorry, it was adjacent. Sorry, it's not adjacent to this vertex, but it's adjacent to this vertex of the edge. So it's there, and then this guy's there. Okay, so that's simple. That's an edge contraction of the graph. Maybe some other examples here are good. So this is the contraction of G along E or G along XY. You can do either one you want. Maybe just a really simple example. We do like a triangle, even just a triangle alone works, but let's do a triangle with an extra edge here. And let's contract along, say, this edge for now. Then you're going to get the red vertex and then two other vertices. These two remain adjacent, and then notice here, this edge and this edge are both telling me the red edge is incident to this vertex here, so this actually would give me two edges here. And so that's the contraction there. That's an instance where you'd get multiple copies of an edge. Usually we'll delete that, okay? So usually delete. It just depends on the type of problem you're working on. Okay, so it should either be, it's not always clear from context, so it should be specified. I would say the following. If I'm talking about a contraction, so the contraction refers to both the edge that's being contracted. We also say that this graph, G contract E, sometimes we call that a contraction of G, like it refers to the graph as well. It's just sort of should be clear. If I don't specify, then multi-edges and loops are deleted. I'll say save them if I want them to be saved. Most of the time we don't save them, okay? So the relationship between a graph and its contraction is that much of the incidences and the connectivity and stuff to a degree are preserved somehow. It's not completely clear how all this stuff works, but some of these properties are preserved. And the nice thing is that we lose one vertex exactly, right? You contract along a single edge and one, like I actually often like to think of it as not even, sometimes it's easier to visualize instead of thinking of squeezing this edge together and making all adjacencies. I like to think of like taking this vertex and like pushing it into that vertex. And so I replace this vertex with this one here by like pulling all the information for the green one here, or the reverse direction. It's the same thing. It's just sometimes easier to visualize that way. But the nice takeaway is this is a good thing to do and be able to apply induction. Again, not every property is kept, but we do reduce the number of vertices by one. And so in the contracted graph, you might be able to observe something by induction and say, hey, if I undo this contraction, which by the way, it's not clear like what's the reverse procedure of this. You have to know your graph in advance. Although we will learn something later that's almost an inverse of this. Yeah, it's useful for induction proofs for some problems. Okay, in particular for the first one we're gonna do here. And so this lemma is gonna be called, this is the contraction lemma. All right. And this is for so ultimately we're gonna have a proof to characterize 3 connected graphs. And this is a lemma that will help us do such a thing. Okay, so if G is 3 connected, that's a 3, not a G, or yeah. So if G is 3 connected, then G has some edge that we can contract and keep 3 connectivity, okay? I need to add something here. So if G is not, okay, let me just write it. Let's say if G is a 3 connected graph other than K4. The complete graph on K4 is on 4 vertices is 3 connected by definition. This lemma does not apply to K4. Okay. Then G has an edge, say E, such that G contracted along at E is 3 connected. Okay. So a 3 connected graph has some edge, not every edge, but has some edge whose contraction maintains the 3 connected property. So I can squeeze that edge and remain 3 connected. Okay. All right, so let's prove this guy here.
Just a quick question. There's many properties that are just always preserved by an edge contraction. For instance, like connectedness should always be preserved. Like if you're a tree, you contract any edge and you're still a tree. Like there's a lot of stuff that we don't have to be careful with, right?
That's right. Yeah, there are definitely simple properties. Yeah, I mean, connectivity, just ordinary connectivity, not like, K connectivity, definitely preserved, right? If you've got a path and you contract, then you still got a path. It doesn't break paths. That you remain a tree, yeah, that's also true, that you remain a tree if you contract along every edge. If you'll notice above, how did we get those these things here? These came about from the existence of cycles in the first place, so you wouldn't be getting these again. Yeah, so for simple things, yeah, there's not much to observe. The problem is, or not the problem, but the issue is that those simple properties that maintain easily under contraction, usually we can prove what we want about those with ordinary induction by just pulling off a vertex. Like we don't need contraction to keep tree properties, and we don't need it for connectivity. But yeah, exactly. Okay, so this is by contradiction. So suppose not. In other words, every single edge contraction results in a graph that's not 3 connected. Okay, so suppose not, in other words, no such edge, which means that, so for every edge xy of G, we have the G contracted on xy has a set. So I don't know if it's 2 connected. Actually, after the contraction, it might become only 1 connected. But it has a set of at most 2 vertices. S, let's call that the set, such that, all right, this one's a bit of notation, such that the graph after the contraction minus the set of vertices S is no longer connected. So is disconnected. Okay. So for every single edge contraction you make, the graph's no longer 3 connected, so I can disconnect it with 2 or fewer vertices. Okay, that's what it means to fail the property here. Okay, yeah. Since G is 3 connected though, G minus S, what can you tell me about G minus S?
It's connected.
It remains connected, right? S is a set of at most 2 vertices. G starts out as 3 connected, so it's safe under the removal of 2 vertices. So G minus S, I wrote in my notes here that S does not disconnect G, but what that means is that G minus S is connected. Okay. So what this means is, okay, yeah, in some sense it's more important. So S doesn't disconnect G. So what that means, but then S somehow disconnects this graph here. So this tells you something about this set S, right? So this set S is potentially 2 vertices that live in G, and they disconnect things in G contraction. But it didn't disconnect this thing, but it does disconnect this guy here. So what it tells us is that what's the difference between G contract XY and G? That new vertex that's been introduced, the contraction vertex, that's got to be an S. If it's not an S, then S would be good enough to disconnect G, which it doesn't. So the new vertex, VXY, has got to be an S. So thus, V sub E, let's call V sub XY, we didn't name it E, is in S, okay? Otherwise, S, well, okay, I mean, I just said it there. Otherwise, it wouldn't disconnect G, XY, which it does by definition. Okay. Okay, so that's in that, and suppose, oh yeah, okay. What am I getting wrong here? Yeah, okay, let's actually go up here. I said something wrong here. This here, now we can use this, actually update this observation here. So VXY is in S, but there better be another vertex in S as well. So there is another vertex in S. Why is that? Well, if S just had a single vertex and it was VXY, then XY would disconnect S, would disconnect the original graph G there. So, removing this contracted vertex disconnects this graph here. That's equivalent to removing the 2 endpoints of the original vertex in the original graph there, right? It has the same effect, which would mean that I had 2 vertices that disconnected G, which I don't have. So there's got to be some other vertex in S that in order to disconnect this guy, right? So then I said this has a set of at most 2 vertices, S. It has to be, it's actually equal to 2. You have to have 2 here, it turns out, right? Otherwise, after this observation, we find out that you need a second one. So there's another vertex, I probably named it Z in S. Yeah, otherwise, X, Y, just the 2 vertices disconnects G, which is a contradiction. Okay. Okay, so now I'm going to use a term here that I didn't define here, but I'm going to say any vertices separated by S in GXY, right? This S disconnects this graph here, are separated by X, Y, Z in G. So let me explain what I mean here. Someone guess what I mean here by vertices being separated by S. So S disconnects the graph. Two vertices are separated by that if they're in different components. That's all it means, that they're witnesses for it not being connected, right? They're separated, okay? We use this term a ton. Sometimes I'll literally say separated to mean disconnected. But when you say separated, you really should be referring to two vertices or a subgraph and a vertex. It's just two things that are no longer joined to each other, okay? So not joined by path anymore. Good. That's a very standard term in connectivity. It's, you know, it's very descriptive. It just avoids having to say that any two vertices in different components of gxy minus s, that you're just talking about being separated by a cut set. Actually, that's another term we use here. Maybe I'll put that here as well. This thing we call a cut set, or sometimes we call it a vertex cut. That's a set whose removal disconnects something. Just be careful. We also had the term last time cut vertex. A cut vertex is a vertex cut of size 1, right? Okay, so it can be a little irritating here. So maybe cut set's a little safer here. The reason we like to say vertex cut though is because they're also edge cuts, right? So that's a set of edges that remove. And fortunately, a single edge cut has a nice term, a bridge, right? A very descriptive one. We don't actually have a nice term for a single vertex cut, so we call it a cut vertex. But yeah, anyway, it's usually it's not too confusing in context. But anyway, so I'll use those terms occasionally. Okay, so all right. So this part here was basically a similar observation to before, that S is, I mean, how does S look? Let me just, so S up here, we observe that S contains the vertex of VXY, that special contracted vertex, and another vertex Z, that's S. And this separates or disconnects G contract. And if this disconnects G contraction, then it also contracts G, disconnects G if instead of removing the vertex VXY, which doesn't exist in G, we remove its original two vertices, NZ, has the same property there. If you're not seeing this immediately, think for a moment. If there were you had every component, I mean, if you had a single component left over when you remove G from G, this thing here, then that single component would be everything in the contraction graph as well, okay? It would only be one component. Okay, so now I wanna make a special choice here. Notice that, oops, this all holds for any edge XY, right? For any edge XY, we can contract it, and then there exists a set of two vertices that disconnects the contracted graph, okay? So I don't, you know, Z, where's Z? Z here, it depends on the choice of X and Y, but there always is a Z for every edge XY. So what I wanna do here is choose XY, that's an edge, and Z. Keep in mind, there might be multiple choices for Z there, such that we have a component C in the contraction graph minus S. So this is disconnected. It has components. We have a component of minimal size. Okay. So this is, we're going over a bunch of different graphs and a bunch of different edge vertex removals, right? So every single way of choosing an edge, contracting it, finding every single way of finding a vertex that disconnects it after removing V, X, Y, and Z. Each time you do that, produces some components. Check across every single one of them and choose the X, Y, and Z and C, so that C is of minimal size across everything. Does that make sense? It's a finite scenario. This C, there does exist a minimal component. And what we'll do is we're gonna find another cut with a different edge X, Y, and Z with a smaller component, and that'll be our contradiction. It'll mean that the graph that was contracted was actually 3 connected, because we can't find, this edge doesn't exist that finds a minimal, okay? It doesn't mean that every edge works, it just means there's no minimal one here. Okay, so we got that. Okay, so yeah, maybe now it's easier to start looking at pictures here. So now we're looking in G here, but we can just the same look in G contract if we want. So here's the edge XY, and here's Z. And we know that this disconnects G as well because the contraction on here with Z disconnects G contract, okay? So we can talk about the component C here in either graph. So here's C. C is the same here in this graph here as it is in, let me write G minus S. It's the same exact C either way. We can look in the original graph when we remove X, Y, and Z, or we can look in the contraction when we remove V, X, Y, and Z. We get the same C here. Okay, so this is the one of the minimal ones here. And let's let V be a neighbor of Z in C. Okay, so I put a vertex here, V, that's a neighbor of Z there. Does such a thing exist? Yes. If there's no vertex in C that's adjacent to Z, then there's no reason to delete Z. Like I can already get away with deleting XY to disconnect C. Like this, there's always got to be an edge going to each one of these guys here. Otherwise, why do I even need to delete that to disconnect the graph? Because deleting, Y and X would delete everything that could get across if nothing went through Z. Does that make sense? I don't need to delete Z in that case. Then Z would just be part of like the other components over here, but it couldn't be a part of this guy here, okay? So there's got to be, which exists as otherwise don't need V, the vertex V. Okay, so now, this edge VZ is going to be my candidate to replace XY. Okay, so now, let's see here. Yeah, VZ can also be contracted to get contract VZ, which is not 3 connected, right? Every edge contraction in G results in a graph that's not 3 connected. So we could have used this one as well, okay? So as before, there exists a W vertex such that, right? So in the contraction graph is not 3 connected. So there's a set, oh, I see. Maybe using the letter V was not the best choice here because V sub VZ is a little bit annoying, right? When the name of the contracted vertex is usually V, but I'm not going to change it. Otherwise, I'll make a mistake here. But the contraction of this edge results in a graph that's not 3 connected. Therefore, that not 3 connected graph has a cut set of size 2, as we argued before. That cut set of size 2 must include the vertex created by the contraction here, plus some other vertex W, right? It can't be of size 1, as we established before. So this W is this for the same reason that Z existed. So such that this set VZW disconnects G, right? Because the contraction of this edge as a vertex and W disconnects G minus G contracted. It's the exact same argument as before. There's nothing new here. So these 3 vertices also disconnect G. I only care about disconnecting G at this moment here. Okay, so let's draw this picture here. So this is just an analog of the one above, where now we have V and Z and then W. Okay, and let D be a component of G minus VZW that does not contain X or Y. X or Y vertices still exist. Notice one thing here. It's possible that W equals X or Y, right? W is just some other vertex that's not V or Z whose removal disconnects the graph. It's possible that W equals X or Y. So maybe I should put it here. So W is in here, allowing W equals X or W equals Y. It doesn't cause any problems though. okay? Because let me draw the edge xy over here, and it's in some component, right? X and y are definitely in the same component together because they're joined by an edge, or x or y is equal to w, and then that component like just, you know, looks like, and here's, I mean, it could be like this. These are two alternatives. So this or this, one of these happens. Does that make sense to everybody? Like the, you know, x or y can't both be equal to w, and x or y are definitely not equal to v or z. I mean, just by the, if you go up to the picture above here, like here it's illustrated correctly. You have x and y separate. Z was an additional vertex, and v was something in this component after the removal. So v can't be equal to either of those. Okay, so it's either x or y are together in a component, or x or y is in a component not by itself, but you know, like it, you know, there might be other stuff in here. But this is when w equals x. You can have one of these two scenarios. I don't care about either of these though. I want D to be a component that doesn't have x or y. So there's some other component. I'll write it over here, D. That's what I care about, that D there, okay? Okay, so now my goal here, this is a little tricky here, is to show, I'm gonna actually write this, want to show that D smaller than C. That would be a contradiction, right? C, remember before, C was a component chosen very specifically that it was the smallest among every different way of separating the thing there. If D is somehow smaller than C, then it's a contradiction because it would have said I should have chosen this one instead in the first step here, okay? Okay, so why is that smaller? So let's observe that every neighbor of V in D is also a vertex in C. Okay, you can think of C as it's a component in some disconnected graph. Excuse me, but it's also just a set of vertices. And you can just think of it as a set of vertices in the original graph, right? The vertices that span that guy there. So let me draw a picture here. So any vertex in D here that are adjacent to V, do there exist vertices like that? Same argument as before. If there's no edge coming out of D going to V, then I don't need to remove V to make D a component. So there exists at least one red edge, right? So, and every one of these neighbors that's in D is also here, looks like this, okay? The reason for that is that X and Y are not over here, right? They're not in here. I specifically chose them over here because these let's see, what do I want to say here? That doesn't seem to be an issue right away. Okay, let me try and do an illustration here. Let's suppose that there's a neighbor of V here that's not in C. Yeah, okay, it is because of that, sorry. If this guy is a neighbor of V, where does it live in this picture above here? So neighbor of V is either inside of this blob here, or where else can it be? It can be one of these three vertices. There's no neighbor of C like over here because that would be inside the component there. So it's inside of this component here, or it's X, Y, or Z. But the neighbors of the neighbors of V in D don't include Z, and they don't include X, and they don't include Y. Right? And so now, what I want to say is that what it means is that everything reachable in here, so from Z, everything that I can travel to, I mean, D is a connected component, is also inside of this one here. Okay, so like everything inside of D is also inside of Z. Okay, I'm not going to write all those details out, but if there's something in D that's not in C, I mean, I can't even state it because it's just like obvious, right? Because like this component here, you can't, if I can escape from it, and then I can escape from this one too, and it's not a component, okay? So, all right, yeah, sorry, maybe that's a little hand wavy, but this implies that D is contained in C, right? There's an extra step here. It's not just all the neighbors, but everything reachable is the second step of the argument. Okay, so great. D is a subset of C. That means it's a likely candidate for being smaller. Why do I actually know it's smaller? So thus, I'm going to write this D smaller than C. But why is that? What am I actually, what's the key?
V is an element of C that we know is not an element.
Yeah, exactly. We definitely lost one element, V, right? V was in C, but it's not in D, like because I moved it over to the cut here. So it lost that one vertex, and it didn't gain anything, right? We argued nothing was gained there, because all the like potential gains, I like this, like maybe see it, the potential gaining vertices were Z, X, or Y. But we carefully chose D that it was not V, Z, X, or Y. It can't be Z because that's in the cut. And X or Y are in just some other component. Right? We just said, don't let it be that component. Okay, so we made D smaller than C, and that's a contradiction to the choice of X, Y, and Z, and C at the end there. Okay, so that ends the proof. So there is some edge, right? This is pretty non-constructive, but we do find an edge that'll disconnect the, we can contract along. Okay. All right, so this is like part of a characterization of three connected graphs, but it's not the full story. So for a characterization, I want an if and only if. So let's prove the characterization theorem now. Yeah, so theorem. So G is three connected if and only if there is a sequence of graphs G0, G1, up to Gn, I guess I said, yeah, such that we have the following two simple properties are satisfied. G0 is K4, and Gn is the graph G. And what's the connection between the any two consecutive ones, like Gi and Gi plus 1? So for I at most strictly less than n, we have that Gi equals Gi plus 1 contracted along some edge xy, where xy is an edge. I mean, you don't contract along anything other than an edge, such that the two end vertices of it have degree at least 3. Okay. This one's a little hard to unpack, so I'll run an example here. But what this says is that, I mean, there's two directions to it. It says if you're 3 connected, that you can start with G, find an edge whose two end vertices have degree 3, contract it, and then repeat the procedure until you eventually reach K4. Okay? If it's 3 connected, you can do that. You can find that. That's actually will be easy to find. The reverse is less clear. The reverse is if I give you this sequence starting with G0 and Gn, and I tell you that the next one, I mean, it's next is sort of weird here, comes from like undoing a contraction. I mean, I just relate these two graphs directly. And I know that at each step I had this property here, that the two endpoints were at least 3. Then actually that means that G was 3 connected. Okay. Now, once we prove it, it becomes kind of clear, because what we're going to show is that 3 connectivity is preserved at every step here. I mean, that's maybe not the surprise, right? It's not that you like do this procedure and magically at the end, oh, voila, you're now 3 connected. You're actually staying 3 connected the entire time. So it's kind of easier to see that. But yeah, so you either can find this with a 3 connected graph, but what this also says is that you can build up every graph that's 3 connected by starting with a K4 and then imagining a graph whose contraction along 2 vertices with this degree created the graph, the current graph that you're at, okay? It's a little hard to describe how to undo this, because it's not saying that you take an edge and like pull it apart and make sure you have degree 3 on both. Like it's not really well defined how to undo it. Like there's multiple ways in which the contraction can, multiple ways in which you can undo a contraction, right? You don't know what you started with. But. Okay.
Wait, I have a quick question. How can we have, so 2 vertices X and Y, like what if their degree was actually 3? Wouldn't that be an issue? Because then they're like, Oh, because when you contract, it has 4. Never mind. I take it back.
Yeah. Right. Yeah, exactly. So, I mean, even if like, so one issue, yes, is if these degrees aren't high enough, the contraction may not leave you with vertices with high enough degree to be able to repeat this procedure. But let's do a contraction of a specific graph. Again, I'm going to go in the natural direction, but after we've done it, we can look and see if it was preserved here. So let's take this, it's actually a hypercube, I guess, but and I claim that this is 3 connected. And how do we do that? Well, I mean, how do you find this sequence? I don't know. Like, this doesn't tell you how to find the sequence. It just asks if it exists. Here I can find it. It's not that hard, just by examination, and then we can examine that it worked here. So I put this circle here to mean I'm going to contract along that edge there. Okay. So if I contract along that edge, I lose 1 vertex, and my new picture is like this. So these guys go here and here, right? That's this edge and this edge, and then call me out if I make a mistake here, but I think I'm good at this step here. So that's what happens when I contract there. Next, I'm going to contract there. And so the one thing we should be observing here is every time I do this contraction, both end vertices should have degree at least 3. This is 3 and 3. We're okay. This is 3 and 3. We're okay. So this one becomes, I think this. Looks good. Oops, it's pretty bad. That's the contraction along that one there. Now I'm going to contract here. I'm still 3 and 3. I don't think I'm going to get anything other than 3 in this case, but so that one gives me right when I pull these two together up here, this top vertex becomes degree 4, as Van observed, right? We lose a degree on both sides from this guy here, but we preserve 4. So we do keep our degrees up high enough. And then I think if we contract here, we're just going to get a K4. And that's the end there. So here's the contractions that actually produce a K4. And if I gave you this list here, like this sequence, and said, oh, look, I produced G, and here's the sequence. Here's K4, here's G1. What's the relationship between G1 and G0? There was an edge here whose contraction resulted in G0, and the 2 end vertices were of degree 3. Same thing here. I can check that this G2, is related to G1 in the correct way according to the theorem, and so forth, so on and so forth. So I can check all these steps. Not that they're reversible, but that they obey property 2. And the conclusion then would be about this graph what? That it's 3 connected. I don't know that it's 3 connected in advance, but this sequence here evidences that it's 3 connected according to the theorem here, okay? Again, in practice, this is not particularly useful because I mean, if I could start here and, well, okay, no, sorry. It is useful now that we know that it's an infinolive. Because what it says then is if I start with G, and if I can find these contractions, which again are not easy, but it's easier than undoing them, right? If I've like tried to say, how do I build G from G naught? That seems incredibly hard. But arriving at G naught from G, which is Gn, it's still not easy, but like at least the procedure is reasonable to attempt. And if you could do that and then double check that you're okay, you'd get your 3 connected. Okay, so I want to get through the proof here if I can. So the first direction, I'm not even going to write out the proof. The first direction is suppose you have the sequence. Why are you 3 connected? Well, if you have the sequence, it starts here and ends here, and at each step, in reverse, you contracted an edge here with both endpoints of degree. What am I trying to do here? No. It's not even that. It's not even that. Suppose we have a sequence. Yeah, what am I saying? That's not the direction I want to do. The forward direction is easy, and this one I'll say in words. If you're 3 connected, does such a sequence exist? Yes, by the lemma. The lemma says if you're 3 connected, there's an edge that you can contract and remain 3 connected, right? I can keep repeating that procedure. If I repeat that procedure, I'm losing vertices at each step. Where does this procedure have to stop? You can't end up with a graph on no vertices because that's definitely not 3 connected. So you've got to stop in what would be the smallest 3 connected graph, which will necessarily, actually this proves it, but will necessarily be what? K4. You have no choice but to stop in K4. There is one small caveat. You have to double check this desired degree condition. I'm going to skip that, right? That should be obeyed in the thing. You should check that when I do this edge contraction, that actually the 2 endpoints have to obey this property as well. But that follows from the 3 connectivity, right? If you get a vertex of degree 2 in the resulting graph, then you're not 3 connected. Delete the 2 neighbors, right? So this is automatically satisfied that you're 3 connected each step. Okay. So that one just follows from the lemma. Let's say via contraction lemma. I don't want to say more than that. Okay, so now the weird one, suppose we've got this sequence. G0, G1, up to Gn satisfies 1 and 2. And so in a sense, this is the useful one, right? I give you the sequence, everything is obeyed. How do I know that this is 3 connected from that? Okay, so we show that if GI is 3 connected, then so is GI plus 1. Okay. Keep in mind, this is not what we did in the lemma. This is the reverse, right? In the lemma, we said there's an edge you can contract and stay 3 connected. The relationship between GI and GI plus 1 is that GI plus 1 contracted along an edge XY is GI. So this is saying if the resulting graph is 3 connected, then the starting graph here had to be 3 connected. In general, that's not true. In general, there are graphs that are not 3 connected who, after contracting, increases my connectivity, right? That could happen. But here, I want to say that, oh, basically based on the degree condition, XY, if it were chosen here, this graph here is still 3 connected. And still this like past and future tense is maybe not best to say here, that this is still connected is sort of weird, like contraction is a forward property here. If the result is 3 connected, then we started with something that was 3 connected. Okay, that's what we need to prove. That'll prove the theorem. Because then, of course, Gn is 3 connected. Okay, so I mean, this is an inductive argument, but does it start? Yeah, I mean, G0 is 3 connected, right? G0 equals K4 is 3 connected by definition. So, you know, we're hoping to prove this guy here. So now we'd want to prove that G1 is 3 connected, okay? But what we're going to do here is suppose this procedure fails at some point. So suppose some Gi plus 1 is not 3 connected, okay? And now we're going to employ a similar strategy to the previous argument there, okay? So Gi plus 1 has a vertex cut, right? A set of vertices that disconnects it, S of size at most 2, right? Gi plus 1 is not 3 connected, even though Gi is, okay? One of X or Y must be, so I want to write this down again. It's really important that we keep in mind the relationship between Gi plus 1 and Gi. Okay. So Gi is the result of contracting this edge XY, and we know that dx and dy, the only thing about them we know is that their degree was at least 3 on both ends there. And we know that this is 3 connected. I'm assuming this is not 3 connected. I mean, sorry, this is not 3 connected, and I want to get a contradiction. I'm going to contradict the degree condition here. That's what's going to be contradicted, okay? So at least one of the vertices X or Y is in S. Is in S. Otherwise, S is a 2 cut of Gi plus 1. Sorry, Gi. Okay, what the heck is a 2 cut? It's a vertex cut of size 2, right, of 2 vertices. if S, which is a cut of GI, doesn't include the contracted vertices, then those two vertices just cut GI in the first place, like ignoring the contraction doesn't make any difference. So it's the reverse reason of before, but one of these two guys has got to be in the vertex cut. And then when I contract, somehow it doesn't cut anymore. That could happen, right? That's the change. But if it didn't, if they weren't, neither of them was there, then whatever then S itself, which is just two ordinary vertices from GI plus one that remain in GI, would still cut GI. Okay. Okay, so now let's actually finish this with a picture here. So let's look at GI plus one, and we've got the cut S here, and I'm going to assume that X is in it without loss of generality. I'm going to write Y over here, but the two vertices of the cut, in principle, could be XY. Let me rule that out real quick at least. Okay, so there's some other, there should also be another vertex here, W, in principle, although I don't know for sure. And then let's look at two components, C1 and C2. And then we're just going to get a bunch of contradictions here in each case here. Okay, so we've got components C1 and C2, and this is in GI minus S. So before I do the contraction here. Okay, and remember, contracting this edge here results in GI. Okay, so first of all, if X and Y are in S, then VXY disconnects GI. That's very bad, right? Because like that's a cut of size 1. There's not even a cut of size 2 in it. So this picture is valid here that Y was going out here, and we know that X has got to be in there. Okay. All right, where are we here? If, yeah, okay. If, wait, what? Is this right? So this line here is bugging me here. Yeah, I don't know if we even need this. We're going to establish this actually in a different way in a moment here. Okay, so if X and Y are both in C2, so say, I'm going to put this in a different color here. I mean, this is actually redundant here. I mean, this is what we just argued a moment ago. I don't know what X1, X2 is. X, Y, say they're both in C2 here. That meant that they're not here or here. What we did state this a moment ago, but what's the contradiction here? If X and Y are both in component 2 here. Then this cut S also separates G, right? After contracting this edge here, it's clear that this cut here would still separate. I mean, I said this a moment ago up here. This is just in the picture now here. So then S disconnects GI still, but that's no good, right? Because I've got a vertex over here, and after the contraction, I still have a vertex over here, at least. If I have 2, it goes down to 1. Okay, so that actually, again, tells me this part here. So I'm just actually reproved this with the picture here. Okay, so now, if there exists, we're almost done, a vertex that's not equal to X or Y in C2. Let's clean this picture up. This doesn't happen here. Oh yeah, so let me adjust C2 further. Yeah, okay, I understand now what I'm missing. Here's C2. C2 should be the component containing X or Y here, right? There is a component that contains, they're not both here. We just resolved that they can't both be in a single component together, but one of the end vertices has got to be in C2 there. Okay, so this is comp with X or Y, and then we should, but not both. So if there's another vertex in here, V, in C2, then W and VXY separate or disconnect GI plus 1, right? Because contracting this thing here and W, that will leave a vertex here separated from this vertex V here, which exists. So it wouldn't happen if there's no other vertex here, then this contraction doesn't. So what we're trying to avoid is at every step here, it seems like that W and the contraction of this edge should be as good as removing W and X, right? It seems like that's always good enough. But remember the lesson of the complete graphs. When you remove vertices from complete graphs, they don't disconnect. And it's this analog, similar analog here. V, X, Y, and W would not disconnect G, I plus 1 if there's nothing else in here. Because like this vertex Y is disconnected from this vertex here when I remove X and W. But if I remove X and Y via their edge contraction and W, it should separate the same things, unless there's nothing left over here, right? So I want to rule out the fact that there's a V here. Like V can't be here because otherwise then the VXY and W would still separate even in the contraction, which it can't because it's 3 connected. Okay, so this is also a contradiction. And now that means there's no vertex here except for Y. It means Y is the only vertex in the component C2. And now we've reached our contradiction, because what's the degree of Y then? If it's by itself in a component of this graph here, it is adjacent to X, and it could be adjacent to W. Actually, it's got to be adjacent to W, but it could be adjacent to W. But is there anything else for it to be adjacent to? There's no other vertices in here. So there's nothing else for it to be adjacent to in there. It can't go anywhere else. I mean, it's part of a component. So at least in our picture, the degree of Y is what? I'm going to say at most 2, but it's actually equal to 2. But this is less than 3, which is a contradiction. Okay. So let me, I mean, we're out of time here, but let me just try to illustrate the idea again here. That if G I plus 1 has a 2 vertices that disconnect it, we know that one of those 2 vertices is X or Y and not both. The only way for that to not still be a disconnecting set of GI, so after the contraction, so when I say still, I don't mean XW, I mean the new vertex coming from the contraction and W, because that's essentially equivalent to removing X is removing the result of the 2. The only way that for that to happen is if Y is by itself and its deletion, this component C2 doesn't exist, right, in GI plus 1. That's the only way to get away with it. But if that's the scenario here, then Y's degree was too small. Okay, and so that ends the proof there. Okay. So now we know this thing is valid. That this, if you can find it, this sequence here will tell you that you're 3 connected. Again, not especially useful in practice, but it is the characterization that we have. As I mentioned, there's no characterization of a similar flavor for 4 connected graphs. It would be very desirable to find such a thing. Yeah, I have my suspicions that it's simply not possible. But like, or at least like in a simple way, right? Like it's an issue of complexity theory, perhaps.